Alright, that introduction was a little bit of the Beatles song called Eleanor Rigby. Hope you enjoyed that. Alright, so we're going to go ahead and go through 5.7, talking all about inverse trigonometric functions and the calculus involved in that, mainly with integration. Alright, so the first thing you want to do if you're beginning to study integrals that involve inverse trigonometric functions, you definitely want to review the derivatives of trig functions. So I just wrote these things down here. The ways that you see them most of the time is like here. This is the derivatives we've learned of the 6 inverse trig functions. This is another way to look at it. In some cases, this is real helpful for integration when you're doing a U substitution. So those are things we've already learned before. You just want to review those. So I do want to go over just a couple of examples of derivatives before I get into the integration then. So first one, we're going to do a derivative of the inverse tangent of x over 2. Now you could use this formula directly, which I'll show you in a minute how to do. But for now, let's just do what we've already learned how to do. If you look at the general definition, it's going to be 1 over 1 plus x squared. But we have a function there, so we're going to have to apply the chain rule. So this would go like this. We would say 1 over 1 plus that function, which is not x, it's x over 2. And then we would square that, and then we would multiply that by the derivative of x over 2. Now x over 2 you can write as 1/2 x if you want to, and you can do this step in your head. So what we would have is 1 over 1 plus, this would be x over 2 times itself would be x the second over 4. The derivative of 1/2 x is 1/2. So that's an unsimplified form of that derivative then. So what I'm going to do is a couple things just to show you how to simplify this. Mostly this is a complex fraction, so you could distribute the 2 through the bottom. So 1 times 1 would be 1. The top you would have 2 times 1 is 2. And then you would have 2x squared over 4, which of course you could reduce that fraction. So you would have 1 over 2 plus x squared over 2 then. All right. Now it's still a complex fraction, so we need to get rid of that denominator of 2. So how do we do that? Well, we multiply by 2, but it's a fraction. We have to do the same thing the top and bottom to keep from changing the problem, so multiply the top and bottom by 2. All right, so if we do that, we'll have 2 in the numerator, and then 2 times 2 would be 4. And then, of course, these things would cancel out, leaving you this then. So that should be a nice simplified form of that first derivative then like that. So that will be the answer to the problem. All right, so that's how you would do that with the chain rule. The other thing you could do is if you look at this formula right here, what we're doing is we have the inverse tangent of x over 2. Well, a would be equal to 2. So you could just plug directly into this formula and get 2 over 2 squared plus x squared. So look at that. You'd have 2 over 4 plus x squared very quickly if you did it that way then. So those formulas can be useful, but if you don't know those, then you can just use the chain rule. Okay, and that's what the rest of these problems are going to be doing, it looks like. Okay, secant. So let's just refer to this secant formula right here. 1 over the absolute value of x times the square root of x squared minus 1. And x cannot be equal to -1, 1, or 0 because you have some places where you're undefined. All right, so we just do exactly what the formula tells us to do. We say 1 over the absolute value of x, but the thing is we have a function, so what's going to go there is that should be the sine of x. Okay, so don't put in absolute value of x, put in sine of x. Okay, that'll go there. Then again, we have square root of x squared minus 1. Well, this should be sine squared x when you plug that in, minus 1. And then you have to multiply by the derivative of what's inside, which you can easily do in your head. Okay, I'm going to erase this bit over here. All right, so here's what you'd have. Now, there'd be a little bit of simplification you'd have to do on this one. So it looks like we would have 1 over absolute value of sine x times the square root of sine squared x minus 1, and then the derivative of the sine x is the cosine of x. So that would be an unsimplified derivative. I do want to simplify this a little bit and just show you a couple things, mainly with this absolute value and how you'd need to treat this. So you would have cosine of x over the absolute value of the sine x times the square root of x squared minus 1, like that. Okay? So we're going to look at, what could we do with this? Well, the problem is the absolute value of sine x, you can't just take off the symbols and get sine x, because sometimes we know the sine of x gives a negative answer, sometimes it gives 0, and sometimes it gives 1, so we can't remove that. And for that reason, we really couldn't do cosine x over sine x as a cotangent of x. Okay, we can't really do that, and we can't just put the cosine in absolute value, so you got to leave that alone. The only thing that you could probably do on this is you could rationalize the denominator. I am going to go ahead and just do that, and then we'll kind of see where this leads us then. Okay, so the numerator, it looks like we would have cosine x multiplied by the square root of x squared. Oh, hold on. You know what I did? I totally screwed up here and wasn't paying attention. Okay, so I do this sometimes. Okay, so remember this was sine squared x minus 1. My apologies. Okay, so that should be sine squared x minus 1. And then we want to rationalize that denominator. Okay, like this. Okay, then we're ready to get this simplified then. So the numerator is just going to be cosine x times the square root of sine squared x minus 1, and the denominator is going to be absolute value of sine x, which you need to leave in there, and then the radical would come off, so you would have sine squared x minus 1. So I do see one other thing that I could potentially do with this problem, and that would be you have the fundamental identity, sine squared x plus cosine squared x equals 1. Well, if I rearranged this, I would get sine squared x minus 1 equals negative cosine squared x. So I could replace this with negative cosine squared x. So let's go ahead and do that. So we would have cosine x times the square root of sine squared x minus 1 all over absolute value of sine x, and then we can replace that with negative cosine squared x, and then we'll have one cancellation. Okay, so you could cancel one of the cosines out. You have a leftover negative, so you would have negative square root sine squared x minus 1, and then we would have absolute value of sine x times cosine x. Okay, and there's not one answer to this problem. This is just the simplifying that I chose to do. The other thing that I wanted to kind of show you on this, if you were working with the square root of sine squared x minus 1, well, it is true that that's equal to the absolute, the square root of negative cosine squared x, okay? And you would end up kind of having imaginary numbers with that negative there, and we don't want to get involved in that in any way. I mean, technically, you could go through and you would have this. You could theoretically do that, and then you would have I, and then you would have cosine x. We don't care about that. We're not interested in imaginary numbers on this, okay? So anyway, that would be probably about as much as you would want to simplify something like that if you were asked to do that. Okay, the next two, I'm going to go ahead and work on these next two here. So we're going to do the inverse sine. So the inverse sine, remember, the derivative is 1 over square root of 1 minus x squared. Okay, so again, you have a function, so you have to apply the chain rule. So what that would be is 1 over the square root, and you can refer to this 1 minus x squared, but it's not that, it's 1 minus 1 plus x squared, and then squared, and then you've got to multiply by the derivative of that function 1 plus x squared. So if you're doing that chain rule, that goes in for x in that formula for the derivative, and you got to multiply by the derivative of that function. Okay, so let's do that and see what kind of simplifying we need to do. So this would be 1 over the square root of 1 minus. We could leave that alone, or let's just go ahead and FOIL it out. It's really up to you. It doesn't really make any difference. I'm going to FOIL it out. That would be 1 plus 2x squared plus x to the 4th, all under that radical. And then the derivative of 1 plus x squared is 2x. So then we'll just do this. We have 2x over square root 1 minus 1 minus 2x squared minus x to the 4th. And then I'll write this as 2x over, looks like the 1's cancel out. We have square root of negative 2x squared minus x to the 4th. And that's okay to stop there. Yeah, you could factor an x squared out if you wanted to. So, I mean, it's okay probably if you stop here. I just think one other thing you could consider doing is if you factored out just an x squared, then you would have negative 2 and then minus x squared like that, and that would allow this to come out, okay? So if I do that, and that would come out of the radical, so I'd have 2x over x, square root negative 2 minus x squared. Then you could cross out the x's and you could get this. Okay, so you probably could go that far if you wanted to, and then that would be an acceptable answer for that derivative. Okay? All right, so you got a little bit of simplification that you got to worry about in some of these problems. So the last one's the inverse cosecant, which is negative 1 over absolute value of x, square root of x squared minus 1, is the general formula for the derivative of an inverse cosecant. Okay, you do have a constant multiplied by that function, and you are going to use a chain rule because you have a inverse cosecant of another function, so you have a composition of functions. Okay, so you're going to have 3 times, and then just do exactly what the formula tells you to do. Negative 1, square root, absolute value not of x, but of the function e to the 2x, and then times the radical, you're going to have e to the 2x squared minus 1, and then the chain rule says multiply by the derivative of that function inside. Okay? All right, so we got that function. See, that kind of gets replaced in for x, and then you have the chain rule. Okay, so there's a couple of things we could do with this. We could multiply straight across and get, that would be negative 3. Now, I'm going to talk about this. This, no matter what x is, this thing right here is always going to be greater than 0. Okay, even if x was a negative number, I mean, say that x was negative 1, you would have e to the negative 2. That's still a positive number because it's just 1 over e squared. So what you'll find is this thing could come out of the absolute value because it's positive anyway. So when you got absolute values, you have to kind of think and reason through like that. So I can take off absolute value. Okay, and then under the radical, e to the 2x squared. I see students mess up on this a lot. All you're doing is multiplying the exponent. Or if you wrote it out twice, you're adding that exponent. 2x plus 2x is 4x. Okay, so that's going to be e to the 4x minus 1. And then when we do the derivative of e to the 2x, we do a chain rule on this. So it's going to be itself times the derivative of the exponent. So the derivative of 2x is 2. Okay, so that's what you're doing. It looks like these whole entire things there cancel out. And then 2 times negative 3 is negative 6. And you would have square root of e to the 4x minus 1 would be what you have there then. Okay, so this is a review of differentiation of inverse trig function. Those of you that go on and take Calculus 2, you actually work quite a bit with inverse trig functions, both with differentiation and integration, so it's pretty important to make sure you know how to do this. Okay, we're going to move on now to integration. So I'll move to the next page and let's just kind of go with the integration. So what we're going to be looking at primarily is these 3 integrals right here. And these are basically, if you go to the previous page, this is kind of like you're given this side. So if you had an integral that looked like this, you would be dealing with an inverse sine of x over a integral. If you had something like a over a squared plus x squared, then you would be working with inverse tangent of x over a. Okay? So, I'm going to go through these integral formulas and just do a couple of examples down here of a few definite integrals. So the first thing you got to do as you're learning this is, it's best you try to memorize as many formulas as you can, but you want to see, okay, what does this match up with? Generally, if you see something plus something x squared, it makes you think a lot of this integral, which is an inverse tangent integral, okay? Well, but this doesn't have the form u squared. It has 2x squared. So what we can do is we can factor that 2 out of there. Okay, so we're going to do the integral from 1 over root 3 to root 3, which will work out nicely on the unit circle. And then let's factor this out, say. So you can factor a 2 out, and then what you would have is 1 plus x squared. Okay? Now, okay, really all you got to know on this now is remember that the derivative of the inverse tangent of x, well, that is 1 over 1 plus x squared. Okay, that's on the previous page in kind of the review section here. So see, that is just that derivative right there. Okay, so the more familiar with these formulas are, the better off you are. Okay, well, this is a constant. If I put that 1 in front of dx just to emphasize this, well, then you know that what you could do is pull out that constant out of the integral, like we've learned. So then we would end up having this, which is an integral we know, okay? I mean, that's just this, okay? If you have 1 over 1 plus x squared, which we do, then you're going to end up having just inverse tangent, see? Because there it is right there. You don't need U substitution or anything. So this thing right here, 1 over 1 plus x squared, well, you're going in reverse, so that's the inverse tangent. So what you would get is you would get 1/2 multiplied by the inverse tangent of x evaluated from 1 over root 3 to square root of 3 like that. Okay, now what we're going to do is evaluate the definite integral using fundamental theorem. So 1/2 is a constant, just write it down, and then evaluate the upper limit. So we're going to do the inverse tangent of square root of 3 minus the inverse tangent of 1 over square root of 3. And these things can be easily looked up on the unit circle. So I've got a unit circle over here. And, if you're in higher calculus and stuff, you want to know your unit circle, or at least be able to just, create the pieces of the unit circle that you need. So the key thing on this is we know that the tangent of an angle theta by definition is y over x. So what we're really looking for on this is we're really looking at where is y over x equal to square root of 3. I mean, that's what we're doing here. We're trying to find the angle on the unit circle, the radian measure of the angle on the unit circle where that happens. Okay, well, it looks like if we go to this thing, if we go to pi over 3, looks like what happens is we'd have square root of 3 over 2 divided by 1/2, so that would be square root of 3. Okay, so that is pi over 3. And there's another thing as I go through this that I want to mention about your inverse trig functions. The other thing that you want to pay attention to is an inverse tangent has a restricted domain from negative pi over 2 to pi over 2. So when you're doing this, you're only going to get one answer. That's real important. An inverse trig function is a function. You should only get one answer out of that, but you have to know that the answer has to be in this range. So if you're doing an inverse tangent, you got to be in quadrant 1, or you got to have a negative angle in quadrant 4. Okay, so that's how you figure that out. Okay, so that's real important. Okay, I'll erase that and show you the next thing. So now we're looking at 1 over square root of 3. So the question becomes, well, where is y over x 1 over square root of 3? Okay, the place that's going to happen is here, because you would have y, which is 1/2 over x, which is square root of 3 over 2. So look at that. You get 1 over square root of 3. Okay? So that means the inverse tangent of 1 over square root of 3 is going to be pi over 6. Okay? So we have that. Now we're ready to work this out and get the exact answer. This is 1/2. We've got a common denominator here, so we can multiply this by 2 over 2. You can do that in your head if you want. So that is 2 pi over 6 minus pi over 6. So that would end up being 1/2 times pi over 6. So the final answer to this definite integral would be pi over 12. Okay? So that's how you would work that out. Now I'm going to, as I go through this, I think it's worth doing. You can always fast forward through the video anytime you want to, but I always like to take the time when I'm going through this to remind you of how your TI calculator can be used to check your answer on this. So let me show you a couple of things on this. Let me pull up my TI and I'll show you how you do this. And make note of this too, because I mean, if you're working on problems, on homework, you're doing a test, if you're allowed to use a calculator, then you can check your answer on a definite integral. So basically this is what you would want to do. You would want to go back and graph the original function. And that original function is 1 over, and then you have to put this in parentheses, 2 plus 2x squared. You have to get that set up exactly the right way. Now we're going to square root of 3. I think square root of 3 is about 1.7. 1 over square root of 3 is some decimal. So what I'm going to do for that reason, since we're going from here to here, it makes a lot of sense to do the window like this. We could go 0 to 2. Scale however you want to. I'll just scale by 1/2 like that. And just experiment with y. It doesn't probably have to be very big. I'm going to go -2 to 2 and do that. So I'll go ahead and graph this and see if that looks like a good curve. Okay, so actually I'll go ahead, it'll even look better if I go -1 to 1 like that. Okay, so that would be an excellent window to use on this then. Okay, and I'll slide these things over just to kind of have a record of this. So now I graph this, and what I do once I have a good graph here, oh come on, is that thing not moving? There we go. Okay, you want to go second, trace, to open up that calc menu, then option 7. It'll ask for the lower limit. Okay, if you go back and look at the integral that we're working on, the lower limit is 1 over square root of 3. So I'll just put that in, 1 divided by square root of 3. Okay, press enter. The upper limit is square root of 3. And the nice thing is you just put it in. You don't have to work out the square root of 3. Just let the calculator do that for you. Now it's going to shade that area under the curve. This would be 1 over square root of 3. This would be square root of 3. And that gives you this approximate answer on the calculator right there of 0.26179994. Okay, so really all I got to do, see, is I just got to do this. Okay, now I can clear my screen, and if I just go like this, if I go pi divided by 12, see, that matches up. It's the same answer. So that's how you verify that you have the right answer to that problem. Okay, so I think it's real important to work with this stuff enough so that you know how to do those things and check your answer. Whoops, okay. All right, so I'm going to leave those things up there just kind of for a record if you want to do that. If anytime you want to pause the video and do something with your graphing calculator, you're more than welcome to do that. Okay, so I'm going to erase kind of all the scribbling I did here. And let's do this next problem and see kind of what we've got going here. Now this one, if you were to go all the way back to the first page, this is the answer to a derivative right here. So on the first page, we ended up having this formula for the derivative of an inverse secant. So that's what this is. You don't need to do U substitution on this or anything. It's just, hey, we know what that antiderivative is. The antiderivative of 1 over absolute value of x squared minus 1 is the inverse secant of x. Okay, then we're going to evaluate that from 2 over root 3. So the rest of this is just using the fundamental theorem of calculus. We'll need probably our unit circle on this too. Okay, so here's what we do. Plug in the upper limit, so we're going to have the inverse secant of 2 over root 3, that will work nicely on the unit circle, minus the inverse secant of 1. Okay, let's talk about what a secant is. So the secant of theta, by definition, is r over x. Okay, and these are both positive numbers. Anytime you're doing an inverse trig function of positive numbers, so these two numbers are positive, that means you're going to be somewhere in quadrant 1. So we don't have to worry about the domain and all that kind of stuff, really. So what we need to do, in a sense, is just figure out, okay, where is r over x equal to 2 over root 3? And remember, in a unit circle, r is 1. Well, it's going to be one of these two places here. It's either going to be at pi over 3 or pi over 6, okay, because you're just doing r over x. Well, this is the one with the square root in it. So if I did 1 over the square root of 3 over 2, okay, you're doing the reciprocal, so that would be 2 over root 3. So yes, that would be pi over 6. Okay, so we know the inverse secant of 2 over root 3 is pi over 6. Okay, and then we think about basically the same thing here. If we're looking at the inverse secant of 1, we're just asking the question, where is r over x on a unit circle equal to 1? Well, that would be if x is equal to 1. You just have to, we already know that r is 1. So where on a unit circle is x equal 1? Well, it's here. Okay, so that means the inverse secant of 1 is 0. So your answer to this problem would just be, it looks like pi over 6. That's a fairly simple integral to do. Okay, now I'll go ahead and check this real quick on the calculator. You can bypass this if you want to and move forward if you'd like. But it's worth going through, and I am going to do this on the definite integrals on this section. There's a few more we'll probably look at. So we would graph like this, 1 divided by, and for the absolute value, you have to go math, number, ABS, like that. And then you would have just put in absolute value of x like that. Now I do need to insert a parenthesis. That entire denominator needs to be in a set of parentheses. So, okay, so I've got absolute value of x, and then I've got square root of x to the second minus 1, all under 1 radical, like that. So that's what we're looking at, and we're looking from 1 to 2 over root 3, okay? So 2 over root 3 is a number a little bigger than 1. So, you can always kind of check this if you want to. So if I go 2 divided by square root of 3, it's 2 divided by 1.7 approximately. So it's a little bit bigger than 1. So this kind of gives you a little bit of a sense for how to set your window. So I think what I'll do is I'll just go 0 to 2. I'll just do the same thing. Let's just graph what I've got here and see if that's good enough. The y's need to be bigger, so I'm going to go like this. I'm going to go, you got an asymptote probably showing up on here. So let's go something like negative 15 to 15, scale of 5, and let's see what this looks like. That's probably too high. I'm going to adjust that one more time. Let's go, I mean, it doesn't matter, but I like these things to look pretty good when I'm teaching this. So let's go negative 2 to 2, like that. And we can even go 0 to 2 if you want to. So I am going to do that. Or, I'm sorry, 0 to 10. Okay? So let's go with this viewing window. And let's go to this graph and let's see what happens. Okay? So we're again going to go second trace to open up the calc menu. Option 7. Lower limit in this problem is 1. Upper limit is 2 divided by square root of 3, which is a little bigger. and it shades it in, and it gives this approximately. So it's given approximately 0.5230373. Okay, so that's what's coming out there. Okay, all right, and then what you want to do is just simply go through and, well, our answer was pi over 6. So what is pi over 6? It's the same thing. Who would have thunk? All right, see how cool that is? You can go through and you can easily check your answer on these problems. Okay, all right. Let me take a look at, we'll go ahead and move on to the next page. Those are a couple of little bit simpler examples of some U substitution, or I'm sorry, integrals, definite integrals without U substitution. Okay, I'm going to do a couple of more of these, and two more indefinite integrals, and I'll let you kind of pause the video and see if you can work a couple of these out. That's always helpful, I think, to students if they do that, and you should do that. Okay, so the first thing I'll do on this is look at the structure. Okay, earlier in the notes I gave you these three formulas here. So you have something plus something squared. It's a pretty good bet that it goes with this formula right here. So what you could do on this is you could rewrite this as the integral of dt. 25 is 5 to the second. 16 is 4 to the second. And these numbers don't have to be perfect squares to use this formula, but if you see perfect squares, there's a pretty good indication that you're going to use this. Okay? So this is A. So A is just going to be 5. That shows up there, see? And then U is going to be this thing. U is what's being squared. Okay, right there. So it's probably even better on this if you just do this like this. Okay, I think it's probably a little better if you just show this like this. Okay, what are you squaring? You're squaring 4t to get 16t squared. Okay, so that part right there would be what U is equal to. So U is equal to 4t. Okay? All right, so we got everything matched up, and then we just do exactly what this formula says to do. So the formula says do 1 over A. So A is 5, so we have that. Then we have the inverse tangent of U, which is 4t over 5, like that. Okay? So that should be the antiderivative. That's the value of that indefinite integral. Now, how do you check that? If you wanted to check that, you'd have to do the derivative and see if it worked out okay. All right? So that would be how you do that. Just identify A as 5, identify U as 4t. Okay, then you've got your solution. Okay? Okay. All right, let's move this next one. Okay, so the next one, you can pretty easily tell that it's just backwards of the derivative formula right here. 5 is a constant, so you could simply just remove the constant. And you could write it this way if you want to. I mean, I'm just doing this because you see it may be a little easier. So, hey, there it is. We already know the antiderivative of this is inverse sine of x. So what you would end up having on this one is 5 inverse sine of x plus c. And by the way, the teacher did a really stupid thing here and forgot to put the plus c on that. Don't forget that. Okay, so that would be the answer to that problem then. Is what you should get then. Okay, so don't forget your plus c's on that. Go ahead now and you can pause the video if you'd like and go ahead and do these three integrals. And I'll give you a little time to do that. Just pause the video. And I've also got these formulas here. Each one of these problems has something to do with these. They have the right structure. So go ahead and do those and then resume when you're ready to check. Okay, so here's what you should have got. I went ahead and worked them out. And number 1, inverse sine 4x plus c. Number 2, 1/3 inverse tangent 0/3 plus c. And then the last one, I didn't really use this formula. I could have, I just remembered that the derivative of the inverse secant is 1 over absolute value of x squared of x squared minus 1. But anyway, if you do that definite integral, you're going to get pi over 4. Okay? And just a couple of things to mention on here. If you got these, you can go ahead and forward the video a little bit if you want. So what I did on this, I noticed that this had the same structure, square root of a squared minus u squared. So I know I'm going to end up with this type of integral. I wrote it as 1 squared minus 4x squared. That way a is 1, u is 4x. Then you do exactly what you're told to do. If u is 4x, if a is 1, then all you're doing is inverse sine of 4x over 1 plus c, and you got it. Okay. The next one, 9 plus z squared, follows this one well. We're going to use this structure. Again, 9 is a perfect square. Write it as 3 squared, so it matches up this a squared. Leave that as z squared. So a is 3, u is z. So you would just have 1 over a, just following this formula, inverse tangent of u, which is z, and then a is 3. Okay, so these are just exercises to get you used to using integral formulas of this type. Okay, and finally the last one, say I know the antiderivative is the secant, inverse secant. Fundamental theorem, I do inverse secant square root of 2 minus inverse secant of 1. That gives pi over 4 minus 0. And what I know about the secant of theta, that is r over x. So you're really looking at where is r over x equal to 2 on a unit circle. Well, that happens at pi over 4. And you're looking at where is r over x on a unit circle equal to 1. Well, r is 1 on a unit circle. It happens when x is 1. So that happens when theta is 0. Okay? And some of you may need to review your unit circle a little bit, because super important that you know how to handle these inverse trig functions. Okay, moving on. Now we're going to look at U substitution. I'll do the problems on this page, and then I'll give you a little time to try to do a few of these. So what I've done is have these formulas handy here. These are the ones you're going to be using. And then here's the formulas for a derivative, because it's kind of helpful to do that and look at that as you go. Now, U substitution, you're generally going to have an expression that's fairly complicated. And the thing you always got to do is figure out, what do we want U to be equal to? Well, I'll tell you the clue on this problem. Is I see this 1 plus 4t squared, it makes me think a lot of this. Okay, now that's in the denominator now, so the other thing that I think of is, well, the derivative of an inverse tangent is just 1 over 1 plus x squared. Okay, so we got to do a U sub on here. The correct way to do that is to let U be the inverse tangent of 2t. That whole entire numerator we want to have, and then we would like for du, it would be nice if it just turned out to be 1 over 1 plus 4t squared dt, or something real close. Okay, so we got to do this by the chain rule. Okay, the derivative of the inverse tangent, you can look at this formula for reference, is 1 over 1 plus this function squared times the derivative of that function, which is 2 times dt. Okay, well, we're close. Looks like we're only off by a constant. So what we'd have is du equals 2 over 1 plus 4t squared times dt. So all we got is that extra constant 2. So what we could do is you can multiply both sides by a half if you want to. So you would end up having 1/2 times du. I would cancel that out. And that would give you dt over 1 plus 4t squared. Okay? And that's what we're wanting then. So see, this u part, the du part, turned out to be 1/2 du. So it plugs in like this. U is the numerator. And then this part right here would be 1/2 times du. Okay? So what you end up having then is you end up having this. Your integral is going to be u times 1/2 du. And see, that's a real simple integral to work with then. Okay, now think about that. U sub is sometimes a little challenging for students to catch on initially when you do these things. Okay, so this would be the way to do it. Okay, so now we just plug to do our integral. That would be 1/2 u to the second over 2 plus c by the power rule. Bring the 1/2 out. So you'd end up with 1/4, and u is inverse tangent of 2t squared plus c. So that would be the final answer to that problem. Okay, when you did du, you didn't end up getting 1 over 1 plus 4t squared. You ended up getting 2 over 1 plus 4t squared. That's where that extra 1/2 shows up in that problem. Okay? Okay. Let's see what we're getting ourselves into in the next problem. Okay? Well, let's see. If you were to look at these four, we have a square root. And we have a number minus a function. So this makes me think a lot that this is going to maybe have something to do with this, possibly. And then notice if you do a derivative of an inverse sine or an inverse cosine, you have something that kind of looks like that then. So you got to kind of play with u. Now, if we let u be this, let's just kind of think about what would happen if we let u just be that. And by the way, sometimes you're going to choose the wrong u and you're going to know that. Okay, when we do a derivative of an inverse cosine, you can look down here just to kind of review this. We're going to be getting -1 over the square root of 1 minus the function squared times the derivative of the function by the chain rule. So that part right there, let's see what happens if we let that be u. Okay, du, again, what we want, what's left over? What is left over is this, this, and this. So what we really want is for du to be equal to e to the t over the square root of 1 minus e to the 2t times dt. That's what we hope happens, but it's not going to quite happen. So let's go ahead and do the derivative and see how close we are. Okay, again, follow this formula. It's going to be -1 over the square root of 1 minus the function squared, not x squared, the function squared, times the derivative of e to the t, which is e to the t. That's a chain rule. So look, we're pretty close on this. Okay, we've got, let's work another step out. We have du equals -e to the t over square root of 1 minus e to the 2t. Okay, so we're only off by a constant here, aren't we? Where did I get that 2t? What we want is, I don't know why, that's a dt. Okay, I don't even know what I'm doing. That's a dt. That's what we wanted. What was left over, e to the t over square root of 1 minus e to the 2t dt. That's what we want. We're real close. We're just off by a negative. Well, so if you multiplied both sides of this equation by a negative, look what you would get. You would just end up getting negative du is equal to exactly what we want. E to the t over square root of 1 minus e to the 2t times dt. And bingo, that's what we want. Okay, so what's going to happen then is this part, e to the t dt over the square root of 1 minus e to the 2t, the part that I have in blue, well, that's just going to be negative du. Okay, so here's what your u integral looks like. Okay, you're ready to put it together. The cosine part in yellow just becomes u. All of this stuff in blue becomes negative du. That's a real simple integral to work out. So you would have the integral of negative u du. That's just going to be negative u to the second over 2 plus c. And then you can plug back in your u and you got it. So we would have -1/2. Okay, and then u is inverse cosine of e to the t, that whole thing squared, plus c. Okay, so that would be your answer like that. Okay, you're just kind of doing substitution so that you account for everything. Okay, it's pretty good problems. Okay, make you think a little bit. An integral is like a puzzle to me. It's just like a fun little puzzle. Integration is always a little harder to learn than differentiation is. Okay, so what do we got going on here? Well, again, the key thing to look at is structurally, what do you have? To me, this looks like it might just be an inverse tangent, because you've got 1 plus something squared. So I'm kind of thinking that that has something to do with that. Okay, then I've got this 1 over z thing right here. A couple of things that might help you see this a little bit better. Let's just write this as 1 over z times 1 over 1 plus parentheses ln z squared times dz. And if you write it that way, it'll help you reason out this U substitution, okay, I think. All right, so here's what you do. U, okay, what in the world are you going to let U be equal to? Well, okay, here's kind of the key. I have this 1 over z thing here. Okay, if I do the derivative just of this, I'm going to get 1 over z. So let's try to let U just be ln z. Okay, and we're okay if we end up with 1 over 1 plus u squared. We got it made, because the integral of 1 over 1 plus u squared is the inverse tangent of u. So you want that thing, you got that accounted for, but just the u is going to be that. Okay, well, what's left over? This. Because I want to stress that this whole thing right here is what you want. You want that to be, again, 1 over 1 plus u squared. Okay, well, let's see what du is. Well, the derivative of ln z is 1 over z times dz. So notice we have every single thing accounted for now in our integral. Okay, so here's what we have then. Okay, we're going to end up having 1 over 1 plus u squared, and then the 1/2 dz is du. So now we got it made. Well, we know that in reverse, this is just going to be this rule right here. That's just going to be inverse tangent of u plus c. Last step is to plug back u. U was ln z, so we would get inverse tangent of ln of z plus c. Okay, so that would be the antiderivative of that particular function now. Okay? If you're bored, you can always check your answer on these. You can do the derivative, and you can go back and see if it checks. So if you did the derivative of this and simplified it, you would get that expression in the integral. Okay, all right. So pause here if you need to look over these, because these are a little harder to learn. This is the hardest part of this section, in my opinion, is the U substitution. Okay, so we'll go to the next page. I would like you to pause the video, and let's go ahead and work on these, and let's see how you do. Okay. Okay, so let's check our answers here. I'd be real curious how many people got the last one, because there's some trig there. I mean, if you did a good job in a trig class or pre-calc, the very end of that problem is kind of a typical problem that you teach students how to do in trig, because it's leading up to this kind of thing in calculus. So the answer to the first one would be 1/2 inverse sine of t squared plus c. The answer to number 2 would be 1/4 inverse secant t over 2 squared plus c. And then the final answer to the next one would be 1 over square root of 5. Okay? All right, so we can look at that a little bit. If you got those answers, you've done great, because this is about as difficult as it's going to be, I think, in this section. So pat yourself on the back, and you're done. So what I did on this one is on this first one, we let u be inverse sine of t. Du would be 1 over square root of 1 minus t squared dt. Okay, so we have a real simple integral on this. That's u, that's du. The integral of u du. Power rule, that's u squared over 2 plus c. Then plug the u back in. Now you do need to write it this way. A lot of times I'll see students want to write it as sine negative 2t plus c. That's totally wrong. It's the inverse sign. That negative 1 is representing the inverse. It's not an exponent. So it goes like that. Now this problem 2 had a lot of algebra with the du. It's a little messy what I've done here. But the idea on this is, I'll kind of talk through what I did. So I did let u be this entire numerator, inverse secant of t over 2. So when you do du, and you can look at this formula over here, when you do a derivative of an inverse secant, it's 1 over the absolute value of the function, which is t over 2, times the square root of the function squared minus 1, like that then. Did I forget my 1/2 on that? I may have forgotten something on that, so hold on just a second. I think I did. Yeah, I got something wrong on this. I need to do this problem again. I'm sorry. I overlooked one real important thing, and it's okay because it's a pretty challenging problem, I think, for students to do anyway. So let me show you where I made a mistake. I'm just going to erase all this stuff, and we'll kind of carefully run through this then. Okay, so anyway, that's what you would definitely set u equal to. But here's what I made the mistake on du. So, you're following this formula right here. So, you're going to have 1 over the absolute value of t over 2. Okay, like that, all right? And then you're going to have the square root of t over 2 squared minus 1, but then you have to do the derivative of what's inside, which is 1/2. I think I left that off of that then, okay? So now we've got that, and we need to kind of figure out what we need to do. Well, see, what's left over in this integral is what we kind of hope for, is we hope for du being equal to 1 over absolute value of t squared minus 4 dt. That's what we're shooting for. Well, we're just going to have to crunch out algebra and see where this leads us. So the way I would look at this is, okay, so I've got, let's just multiply straight across. We have 1 over 2 times absolute value of t over 2, and then we have square root of t squared over 4 minus 1 times dt. Okay, I should have put that there. Okay. Well, okay, the 2's do cancel out. Now, the reason why, I'm not going to write an extra step, but technically you could break up this into absolute value of 1/2 times absolute value of t. That part right there, you can do that. So you end up getting 2 times 1/2 times absolute value of t. So that does cross out for that reason, because that absolute value of 2 is positive anyway. So you're going to end up getting 1 over absolute value of t, so we like that. And then we can get a common denominator here, so we'd have t squared over 4 minus 4/4 times dt. So that would be 1 over absolute value of t, square root of t squared minus 4 over 4 times dt. Okay, remember, what are we looking for? We're looking to get this. We're kind of hoping to get that. We're getting closer. We're not quite there, but we do seem to be getting closer. Okay, so I've got 1 over absolute value of t times square root of t squared minus 4 all over 2, because the square root of 4 is 2. Now what you really have is, you really kind of look at this problem, you have 1 divided by 1/2 is what you got there. So you get these complex fractions. You can also do this way if you want to. Multiply the top by 2, multiply the bottom by 2. That's the way I like to do these, is like that. So what we'd end up getting is 2 over absolute value of t, square root of t squared minus 4 dt. So that's pretty close. See, we were hoping for this, but we got this. Well, that's easy. All we got to do, and see all this stuff right here is, I should have been bringing down my du there. Now if I divide both sides by 2, I end up getting 1/2 du is equal to 1 over absolute value of t squared minus 4 times dt. Okay, like that. And now we're ready to roll. Okay, so it looks like u is going to be the part in yellow, and then the part in blue is going to be 1/2 du. Okay, like that. Okay, so what we end up getting then is we're going to end up with the integral u times 1/2 du. So that is 1/2 u to the second over 2 plus c. So that is 1/4 U the second plus C, and then plug back in, and then we'll have the answer of the problem, okay? All right, and what I have here is 1/4 times inverse secant of t over 2 squared plus c. Okay? So that's what I had. I may have got that answer okay. I didn't see that I had done that derivative of t over 2. So right there would be the right answer to that problem. Okay? Okay, it's kind of getting messy. All right, we go down to the next thing. I'll talk a little bit about this next problem, and some of you may need a little trig review on here, but let's talk through the calculus first of all. The calculus is not too hard. You let u be the inverse tangent of t, the whole thing, and then the derivative of the inverse tangent is 1 over 1 plus t squared dt. Okay, so if you look at this integral, that's what u is going to be, and this is what du is going to be. So it's a real simple integral. You're going to have cosine of u du. All right, so that's what you're going to end up having. It's okay to have the cosine because we know that the integral of the cosine of u, we know that is sine u plus cc. C, okay. All right, so we also got to change the limits, okay? So the U substitution is inverse tangent of t. So the 1/2, you're going to do inverse tangent of 1/2, which is an irrational number. You're not going to get anywhere from the unit circle on that, so you just want to leave that alone. Don't do anything with it. Okay, then the inverse tangent of 0 is 0, so you'd have to look at the unit circle. Notice at 0, y over x is 0 over 1, so it's equal to 0. The tangent is y over x. So you end up getting that. So your definite integral is just going to be the integral 0 to inverse tangent 1/2 cosine u du. Now, that's what you got to wrap your head around, is all the substitutions I did gives you that. We know the antiderivative of the cosine of u is sine u. Then we're going to evaluate from these limits 0 to inverse tangent of 1/2. So that would be sine of the inverse tangent of 1/2 minus the sine of 0. We plug in the upper limit, bottom limit, and subtract. Okay, so I would end up getting this. So I just end up getting the sine of the inverse tangent of 1/2. We know the sine of 0 is 0. Now, you don't want to get your calculator out. You want to get an exact answer. So this is something that you learn in a trig class typically. So what you do is you let theta be that. Let theta be the inverse tangent of 1/2. Okay, and by definition, if you're doing the inverse tangent of 1/2, and then that's theta, that just means the tangent of theta is 1/2. Tangent's y over x, so automatically we have y is 1, x is 2. Now by the Pythagorean theorem, we'd have r squared equals x squared plus y squared. So we'd have r squared equals 2 squared plus 1 squared. That's r squared equals 5, so r is square root of 5. Okay, so what do? Okay, ultimately we're doing the sine of that inverse tangent. Well, the sine is y over r, so all we got to do is just do y over r, which is 1 over root 5. Now that's the answer to the problem. Okay, that's a good problem to try to check on your graphing calculator too. I'm not going to do that on this problem, but it's a worthwhile exercise to try to do. Okay, all right, well hopefully this helps everybody with what you're learning in this section, and that should wrap us up. Wow, perfect 1 hour video. That doesn't happen very often. Okay, good luck to you. Let me know if you have any questions.